Welcome to Operating Systems lecture 36. Right. So far we had been looking at logging as a way of ensuring that the system can recover after crash. In other words, ensuring that the disk does not get so corrupted that you cannot even recover your data out of it. Right. So the first thing we had looked at was ordering, where we said that we're going to order the disk operations as they go to disk in a certain way so that we don't lose data. We may have space leaks, temporary space leaks, but they can be fixed whenever. But there were problems with that. The problem was that recovery was really slow, and the other problem was inconsistencies were still possible. So logging was the other way, where basically the file system consisted of a tree, which is your regular file system tree, and a circular log. You will have one transaction at a time. So I'm talking about the ext3 file system. You'll have one transaction open at a time, which you will close periodically. So let's say you close a transaction every 5 seconds, for example, and all the atomic disk operations that are started at any time will be associated, will be tagged with the current transaction, with the current open transaction. The atomic operation will either belong completely to one transaction or not belong to the transaction at all. It's not possible for an atomic operation to be half in one transaction and half in another transaction. Once you close a transaction, you also open the next transaction. So all atomic operations that start after you close the transaction will belong to the next transaction. All atomic operations that started before you close the transaction, irrespective of whether they have completed or not, will belong to the previous transaction. If they have not completed, the transaction will wait for those operations to finish before it starts committing them to disk. All right. So all atomic disk operations are associated with the current transaction, and transaction is atomically committed after closure. And as we saw last time, committing the transaction, before you start the commit of a transaction, you have to wait for all the atomic operations to finish, number one. Number two, you also want to make sure that no atomic operations of the second transaction or the next transaction have started before all the operations of the previous transactions are finished. Otherwise, inconsistencies can result, and we had seen some inconsistencies last time. That can happen. Okay, and we also said, even though, so in this case we logged whole data blocks. Atomic commit of the transaction is implemented by the write of a special commit record at the end of the log, and assuming that this write of the commit record is atomic, you are basically sure that either the transaction will be atomically committed or it will not be committed at all. In which, if it's not committed, it means nothing happened. If it committed, it means everything happened. So there's no intermediate state. So there cannot be any inconsistency, assuming that commit is atomic. So we had been so far assuming that the commit is atomic. We had been so far assuming that the disk actually behaves exactly like the way we expect it to behave. So for example, we assumed that if we tell the disk to write to a particular sector, it has written to it before it actually comes back to us. But the truth, in fact, is that the disks have caches. Right? So in the real world, disks are not really truthful, right? Not necessarily truthful. You can imagine that disks have been manufactured by different devices, different manufacturers, and for better performance, these manufacturers are putting special, volatile caches, which means they're either using technologies, the same technology that you're using for DRAM, for your main memory, into your disk. And so even though the disk has said that it has finished, it may be doing some optimization at the back end where it may not have actually written to the magnetic platter, right? To the actual magnetic platter. So if something like that happens, then all your reasoning about correctness actually goes for a toss, right? Because if you ask the disk to write the log and wait for the disk to respond, and then you ask the disk to write the commit record, and the disk internally has cached the first write, hasn't actually committed to the magnetic platter, and it commits the commit record before the actual contents of the log, then when you recover, you will see that there's a committed transaction, but the transaction's contents may actually be junk, right? So these kind of things are possible, and so ext3 doesn't deal with these kind of problems, but the next file system, ext4, introduces checksums. in the commit record. So the idea is that the commit record will have a checksum or some kind of a one-way hash of the contents of that transaction. Right? So when you are recovering, you can check that the checksum actually matches the contents of the transaction, and if not, then you can say that something fishy has happened, and you shouldn't be actually replaying this transaction. Okay, so that's one way of dealing with these kind of issues. All right. Okay, so as we have discussed logging, we were logging whole data blocks, both data and metadata blocks. Right. So if I were to look at the file system and I was to look at all the blocks in the disk, I could divide the blocks into either they are data blocks, which means they are blocks that hold the contents of the files that the user is actually writing to, and there are other blocks which I can call the metadata blocks. The metadata blocks are blocks like the super block, the inode blocks, the free bitmap blocks, the directory, the blocks that contain the contents of the directory, even they are metadata blocks. Right? So all the blocks that are associated with the semantics of the file system are metadata blocks. All the blocks that are not associated with the semantics of the file system are data blocks. Right? So for example, the contents, the blocks that are storing the contents of a file have nothing to do with the semantics of the file system. Right? So they are metadata blocks, and everything else is metadata blocks. And so far, as we have discussed the logging file system, we are basically saying that we log everything. We log both data blocks and metadata blocks. But notice that logging data blocks is not necessary for making sure that your file system remains consistent. Right? So and the other thing is that logging all data blocks may actually be expensive. If you can avoid logging data blocks and only log metadata blocks, and so you avoid the 2x writes on the data blocks, you only do 2x writes on the metadata blocks, that's likely to be more efficient than logging everything. Right? So that's actually the default mode. So ext3 has two modes: ordered mode, which says log only metadata, blocks, and journal mode, journaled, where I say everything. Okay, and the ordered mode is the default mode. So most people use the ordered mode. In the ordered mode, you only do this logging or atomicity maintenance for metadata blocks, but you need to be careful because imagine if the inode has been committed, but the data block that inode is pointing to has not been committed to the disk, then you will have a dangling pointer in your inode. Right? So in the ordered mode, the invariant that's followed is that you will flush or write to the disk all the data blocks belonging to the transaction before committing the transaction, which contains the log of the metadata blocks. Right? So in the ordered mode, you basically ensure that all the data blocks are written to disk before you commit the current transaction. That's all. So instead of logging the data blocks, you just make sure that there's an ordering relationship between the data blocks and the metadata blocks. And so the ordering relationship is something like this: flush all data blocks before commit, transaction commit. So you flush all the data blocks before you do a transaction commit. Notice that I'm in this ordered mode of journal ext3, I'm using both ideas from the logging idea and ideas from the ordering method. Right? I'm saying I'll flush all the data blocks before I commit the transaction. So let's see what happens if I flush all the data blocks and I haven't yet committed the transaction and there's a failure. What can happen? Well, you have just updated some data blocks on the disk, but you haven't really updated the inode corresponding to those data blocks. So there's really no problem. So there's no, the inodes will probably be pointing to the old data blocks. Or some data blocks have been updated, some have not been updated, but the file system remains consistent. The contents of the file may have changed partially, but the file system itself remains consistent, right? So it's possible that the user wrote 10 blocks, only 5 blocks have been written to disk on a crash, and 5 haven't. But the file system itself is consistent, right? So that's the important thing. So the difference between the ordered mode and the journal mode in ext3 is ordered mode is not concerned about atomicity of full operations. Ordered mode is just concerned about atomicity of all the metadata operations to ensure that the file system remains consistent. It doesn't care about the user side or the user's data. So user is really left to on his own devices to basically make sure that his logic remains correct, right? So that's one thing. Okay, so now let's talk about how does the user. So firstly, I hope we are all convinced that using this method, we can be sure that the file system remains consistent. There are a few things one needs to be careful about. The few details about the ext3 ordered mode. For example, if you let's say delete a block, you cannot use it in a free list. So you cannot recycle blocks before a transaction commit, because otherwise there can be inconsistencies. So there are some details that I'm skipping over, but basically, at the high level, it's basically saying that you will flush the data blocks, and you will, and you will not provide any consistency on the data blocks, but you will make sure that all the metadata blocks remain consistent. Okay. So how does the user? This gives no guarantee to the user. The user is doing something. How does he know whether what he has done has actually been written to disk or not? Right? So for example, I've given you an example of an ATM machine. Let's say your ATM program was running on top of an operating system, and the ATM program said, I want to make this transaction, and he debits my account with some money and gives me the cash, but the debit hasn't actually been reflected on disk. So what's the device that the user has to make sure that the thing has been committed to disk? And so there's a system called fsync, right? Or different operating systems can have different versions of this, and you can say, I want to flush the contents, the data blocks of this particular file to the disk, right? How will the file system implement something like fsync? How will ext3 implement fsync, let's say? In the journal mode. So there are two modes in ext3. There's a journal mode and there's the ordered mode. So let's say in the journal mode, if the user calls fsync, what should the operating system do before it returns from the system call? It should commit the current transaction. It should commit the current transaction, and that's it. Does it need to wait for the transaction to get applied to the file system tree before it returns from fsync? Okay, how many say yes? 1, 2. How many say no? 2. Everybody else is undecided. Okay, none of the above. All right. So the answer is you don't need to wait for it to apply. Right? Commit is enough. Recall that the semantics of the file system is that anything that's been committed is as good as done. It's just a matter of syncing the state to the tree. That's just something that, and that's you can consider it as an optimization, so that the next time you're looking through through the tree, you don't have to go to the log to look at the latest contents. You can just do it from the tree itself. Right? So as soon as you commit the transaction, it's as good as it's done on the disk, and it will persist across power failures. Right? So when you do an fsync, the operating system just in the journal mode just commits the current ongoing transaction, and so closes the current transaction and commits it before it returns.
Sir, in case of recovery, like suppose power failure occurred in this state after fsync, sir, we should want that the tree should be right.
Okay, so let's say if there's a power failure after fsync, and you recover, then the question is, shouldn't you require that the tree is correct? Well, not really, right? I mean, at recovery time, you will just you know that there's a log, so the tree could be in
log is already showing committed, right?
so the log is showing committed, but the log has not been freed. Recall that the ext3 file system first commits the log. After the commit, it starts applying the log to the file system tree. If there's a failure in the middle or at the beginning of this application, it's okay. You haven't freed the transaction. You've just committed the transaction. You will free it after the transaction has been applied completely to the file system disk. At that point, you will free the transaction. So in the journal mode, it's enough to basically commit the transaction and then return. So, but an fsync is a relatively slow call, as you can imagine, because an fsync cannot return without actually making a disk access, and that's expected, right? Unless, of course, there were no dirty blocks in your block cache, in your buffer cache. On the other hand, most other system calls which access the file system don't actually need to go to the disk, because we are using a write back cache for the buffer cache, right? So the fsync is a device for the user to basically make sure that that things are getting flushed to disk. So what happens if the user is using fsync too often? System becomes really slow. Your write back cache becomes completely ineffective. You basically you start looking like a write through cache. Let's say he's doing fsync after every system call. It's basically like saying that every system call becomes one transaction. So the system becomes really slow, right? And it becomes even slower for something like a transaction from something like a logging system like ext3, right? ext3 logging was actually heavily relying on the fact that you're batching lots of writes. You're doing 2x writes, but because you're batching them, the performance is not really 2x slower, right? But if the user is actually calling lots of fsync, you are actually 2x slower. You're writing small transactions to the log, and then you are applying them to the system, to the tree. Okay. Let's see, what about the ordered mode? So if I'm using the ext3 ordered mode, and if the user calls fsync, what do I need to do? I need to flush all the data blocks, and I need to commit the transaction which contains all the metadata blocks, right? That's all. Okay. So what are some types of applications that require fsync, right? That require that data be on the disk before you do something. And most of these, such applications are usually what are called transactional applications or transactions, where an ATM transaction is an example of that, or a bank transaction is an example of that. You basically want that you basically have committed to the disk before you actually display to the user that your amount has changed, or you actually dispense cash to the user, etc. Right? So you would want something like that. And how are such applications typically implemented? Such applications are typically implemented by using what's called a database, right? So database basically maintains all the state, who has how much money, etc. And database is supposed to give you guarantees that if you have said something, you've asked the database to do something, it has actually done it on disk. It has committed the whatever operation that you've done by a commit in a transaction of a database. You basically mean that the data will persist across power failures. So if you're running a database on top of an operating system, as an application, then the only way the database can provide you those guarantees is by calling the fsync call, right? So database is an example. A user space database, or a database running as an application, is an example of an application that makes lots of fsync calls and is likely to be very slow on something like this, right? And that's the reason you would typically implement a database as a standalone system without an operating system below it, right? So you won't implement a database on top of an operating system, because you have two layers of management of disk. It's if the database should optimize itself. So if the database had direct access to the disk, it would have been able to optimize these things much better, right? As opposed to sitting on top of a file system like ext3. Okay. On the other hand, most other applications don't care about persistence for transactions, and so they can run easily, and they don't need to call fsync calls, and they perform excellently on something like ext3.
So a DBMS does it has those privilege levels to actually access the disk directly?
Does the DBMS have the privilege levels to access the disk directly? Well, I mean, So I said there are two ways to implement a database management system, DBMS. One is you implement it as an application on top of an operating system, in which case it cannot access anything. The other way to implement a DBMS is to implement it as a kernel itself or within the kernel, right? In which case it has all the privileges you like. And so what I'm saying is, here's a very good example why you would want to implement in the kernel, as opposed to doing it at the application level. Because if you do it at the application level, you have to go through the operating system interfaces, and the operating system is playing tricks underneath, and then you want certain guarantees out of it, and so the total performance, sum total of performance, is really not what you would like it to be. On the other hand, if the database had complete direct access to raw disk, it would have been able to optimize these things much better. Okay, so that's I'll wrap up the topic on file systems with this discussion, and I'm moving on to the next topic, protection and security. Right? Okay, so we all know that we need we need lots of security or protection guarantees from an operating system. Your files on the shared infrastructure, like the shared lab that we have, shouldn't be readable by other people, shouldn't be writable by other people, and so on. And so you have a notion of these are my files, these are your files. You also have, firstly, you have notion of identities. So there are different identities. Each of us has a different identity in the system, right? So protection and security is made up of three things: authentication, which is a method of saying who is who, right? So our login IDs or some other names basically say that who is behind this action, right? So we have some notion of entities, and we basically have some way of ensuring that this person is behind this action, or this entity is behind this action. This entity is also called principal. So authentication identifies the responsible principal behind each action. Then there is authorization. So this says who is the principal behind. Let's just say this. Authorization is what can the principal do. Okay. So basically says that user XYZ can access files ABC in read mode, and access files DEF in write mode, and so on, right? User root can access all files in ABC in read write mode, for example. So these are all examples of who can do what, right? So that's authorization. Who is authorized to do what actions? And then there's access enforcement. So you have a method to do authentication. Who is behind this action? You have a method to do authorization. What can this principal do? And then there's an access enforcement, which ensures that only legal things are possible, which means only things that a principal is allowed to do is possible, right? So these are the three sort of aspects of protection and security. And if there's a flaw in any one of these, then there's a security attack. So let's say if there's a flaw in the authorization and you can impersonate as me, then you can do anything you like. If you can you can add a flaw to the authorization table and say, I can do something that you're not supposed to do, then there's a problem. And thirdly, even if you have all these things correctly, but if the access enforcement is not correct, then there's a problem. Okay. So let's look at how these things are done. Authentication. Let's say passwords. We all know what are passwords. They are a relatively weak way of establishing user identity. Usually stored. So firstly, they are secret and stored in unreadable form, or not directly readable form. Right. So the way passwords work is that you store, so let's say I have a password on a system, then you will use some kind of a one-way hash. Let's say there's a famous there's a popular one-way hash called SHA-1, and you will apply the SHA-1 to my password, and you will get a large string. Right. And this is the string that you will store on your file system. Right. And this function is what's called a one-way function. So by one way it basically means that it's very easy to get this string from this password, but given the string, it's very, very hard to recover the password, to know what the password is. Okay. So it's very hard to recover. So even if you have the string, you will not be able to guess the password. And so even if you have the string, you will never be able to log in to the system because you'll not be able to guess the password. So that's typically how you will store these things. The best attack, assuming that our cryptographic algorithms are correct, our axioms in in computational theory are correct, then the only way to guess or to break this password-based authentication is through brute force attacks, where you basically go through all possible passwords up to a certain length, and you basically check. And so the way to make this secure is to make sure that your passwords are long enough so that the brute force attacks are relatively ineffective. Right. So that's pretty much mostly how authorization is done. Alternate form of authorization is badges. Right. So everybody has a badge. A badge could be something, a card that you're using to authorize yourself, or it could be a USB device that you have to plug in, etc. The advantage of something like that is it doesn't have to be kept secret. It should not be forgeable or copyable. But if it's stolen, then at least the owner knows that it's stolen and can register a complaint, etc., and or change the authentication mechanism. If you're using badges, there's an interesting paradox that the badges should be easy to make or cheap to make, so that you can distribute lots of badges to lots of people. But it should be very hard to duplicate badges. So it shouldn't be possible that if you have a badge and I just get access to it for for some time, I shouldn't be able to duplicate it. So there should be some technology there that ensures that it's not possible to duplicate it, and yet it should be very cheap to sort of manufacture. Right. So once authentication is complete, you basically all the actions that are performed are basically done with that particular principal's ID. What does this mean in the context of an operating system? It basically means that all the processes run with that user ID. Right. So basically on Unix, every process associated with UID, right? So recall that process control block that we had for every process. So apart from all the other meta information, another information that you'll have is basically who is the user ID of this particular process, right? And that's so whichever process is running, you always know who is the UID of that particular process. So let's see authorization. So who is authorized to do what? First, let's look at what does authorization mean in the most general sense. Authorization is nothing but a matrix where, let's say, you have one row per principal. So these are principals. Let's say this is user A, user B, and so on. And on the columns, you basically have objects. So for example, file A, device B, memory region C, and so on, right? These are all examples of objects that you have. And this authorization table basically says that user B is allowed to access memory region C or not, right? And in what way? So let's say read or read plus write, etc. Right? So that's basically, at a logical level, that's what an authorization matrix looks like, and this is also called an access matrix. So this is the logical representation of who is allowed to access what, but different things, different authorizations are implemented. So this is the logical authorization mechanism, but different authorizations or different authorizations for different types of objects are implemented in different ways. For example, authorization for memory is implemented using virtual memory subsystems like page tables and segmentation, right? So whether you are allowed to access this particular region of memory or not is basically authorized. The authorization is implemented using some kind of a page table. Authorization for a file is implemented in a different way. Okay, so we're going to discuss that very soon. So in practice, you don't store the full access matrix. There are two ways to store the access matrix. Either you store what are called access control lists, or ACL, per object. So here you're basically saying that I will organize things by column. So who all are allowed to access memory C, or who all are allowed to access file A. I'm going to have, with file A, I'm going to have a list of all the users who are allowed to access it, and in what way are they allowed to access it, whether read or write or execute or whatever else I need to do. Okay. So that's an access control list. So per object, so organized by columns. Per object, list of user privilege pairs. All right. So let's now this list can actually become really large. So typically make groups and indicate that this particular resource is accessed by this group. So you organize users into some groups, and you say that this particular file is accessible by this group, so all the users in that group can access it with those privileges, etc. So let's look at it in practice. Windows allows, so Windows implements ACLs per file, very general. So on Windows you can go to the properties of a file and specify a long list of which user is allowed to do what. Right? So here's an example of an operating system that allows very general ACLs. Something like Unix has 9 bits per file, right? And we're going to see what these 9 bits are. So Unix ACLs. So firstly it divides, so let's say, so I'm talking about a file. It divides it into, it divides all principals into 3 types: owner, group, and others. Okay, and read, write, execute. Right. So this becomes so there are 9 bits. There could be 0 or 1. So that's basically the Unix ACL. Every file is associated with one owner and one group. Right. So every file on the Unix file system will say, the owner is user A and the group is group B, and the creator of that file can, or the owner of that file can choose which group this particular file belongs to or is owned by. And then you can have ACLs of this type, which basically say that this particular user is allowed to, so the owner can do these things to this. So for example, the owner can read and write but not execute this file. You may want to say that. The group can read the file but not write to it, and others, everybody else, should not be able to either read or write. So let's say here's an example. This is 1, this is 1, this is 0, this is 1, 0, 0, and this is 0, 0, 0. Right? That's 9 bits to basically implement ACLs. So clearly this has less generality than a complete list that you had on Windows. There's another thing about Unix. There's a special user called root, and root user is allowed to do everything to every file. Right? So for the root, this access matrix is not, these 9 bits are immaterial. The root user can do anything to any file, for example. Yes.
As in the group permission should be a subset of owner permissions.
Should the group permissions be a subset of owner permissions? No. No. See, it's a full 9 bits, so you can do whatever you like. Okay. So that's basically, that makes it. So the advantage of doing this is that you have a bound on the size of meta information that you have. You can store this information. You can hope to store this information in the inode of the file, as opposed to an unbounded list of user privilege pairs, which will be very difficult to maintain. All right. Apart from this, so the Unix also provides an interesting thing, which is a set UID bit on the file. Right. This basically says by default it's 0, so it's the default behavior, whatever you expect. But let's say if this file is 1, then this file, if executed, can run with privileges of its owner. Okay. So every file also has one bit which is called the set UID bit. If this bit is set, then you can run. If let's say I have a file in my directory, but I've set the set UID bit to 1, then I'm basically allowing anybody else to run this program and with my privileges. So for example, this program if run, so recall that I said that any process that user X invokes will run with the privileges of user X. But if this process is executing a file that had a set UID bit set or 1, then this program can also execute with the privileges of the owner. Okay. So why is this required? Let's first understand what's the application. Why do you think this kind of a thing is required?
Because if this file is this executable file needs to execute some other executable files.
If this executable file needs to execute some other executable files, so?
Sir, it should have that privileges of the owner.
Well, I mean, let's say all the other ones are also executable by others, so then there's no problem. Why do you need this? I think all of you are using an executable called setuid, through the course of this project or this course. Can you think of it? Huh? Yeah, all the scripts that you're using on Palasi are actually setuid files, right? So if you want to submit your assignment, so what I have done is I have a script which is living in I have a file which is living in my home directory, whose owner is me, and but when you run it, you have the privileges. That process has the privileges to write into my home directory. Right? For example, it copies files from your home directory into my home directory to make the submission. So how can the process that you are invoking have the privileges to write to my home directory? Right? I said all the processes that you invoke will run with your privileges, and you don't have privilege to write to my home directory. Right? So the way to do that is basically to basically allow this file to be executed with my privileges. Right? So that's what the setuid bit allows you to do. The setuid bit allows the owner to say that this particular logic, I have tested this particular logic and this is safe, and I allow other people to run this piece of logic with my permission so that they can access resources that I could access. Yes?
So isn't that similar to just saying that, for example, if RWX is my privilege, then I'll set the others' privileges also to RWX. So isn't that just similar that my owner privileges are also what the others?
Okay. Isn't it similar to saying that I have an execute bit set to a file? Now, what's the difference between a setuid bit and just saying that this file is executable by others? Right? If I just say that this file is executable by you, you will be able to execute it, but this process that will execute out of this out of your invocation will execute with your privileges, not with my privileges, and so it will never be able to touch my files or write to my directories. Right? So setuid allows you to not just execute the file, but also execute it with the privileges of the owner of that file, which also means that if there's a bug in this program, then you can trick this program into doing things that I wouldn't want you to do, for example. Right? Okay. So also this typically when you do these things, for example, the submit script that we have is not just capable of writing to my directory, it's also capable of reading from your directory, irrespective of what permissions you have for your directory. So if your permissions for your directory are saying that only I can read to this directory, yet this particular process that can run as my privileges can actually access your particular directory. So this process can either can switch between your privileges and my privileges. Right? So how is this done? Well, I said every process has associated with a UID which says who owns this. Actually, every process has two identifiers. One is called the UID and another is called the real UID. Right? And so a process can switch between its UID and its real UID at will, right? So they're using system calls. It can basically say that now I want to run with the privileges of my real UID, and then I can say I want to now run with the privileges of UID. By default, if the set UID bit of a process is not set, then real UID and UID are equal to your UID, who is invoking it. But if it's set, then real UID will be your UID, and the UID would be, let's say, the owner's UID. And so the process has flexibility to switch between the two. So when I want to read from, when this process wants to read from your directory, he should switch to your UID. When he wants to switch to my directory, he should switch to my UID, and so on. Right? So that basically allows you to do this. Okay. Right. The other way to implement access control are capabilities. What's called capabilities. So we looked at access control lists. The other way to do access control is called capabilities, where you organize by rows. Right. So where basically you organize by rows the access matrix. So per principal, list of object privilege pairs, let's say. So user X is allowed to access all these files, or user X is allowed to access. So you store this information in per user as opposed to per file. That's the other way to implement this. Okay. So let's see, what are some examples of capabilities that we know about? Well, here's an example, file descriptors. So every process has a set of file descriptors that basically say that these are the files that I can access, or I have already opened, so I can I can access it in XYZ way. And so basically a process can be thought of as the principal, and all these file or these pointers to file blocks or structures that represent open files can be thought of as objects, and you're basically storing file descriptor table. That's your capability list. What are the capabilities that this process has? So some advantages of capabilities are that, let's say I spawn a new process, so it's very easy to delegate. So if I have some capabilities, I want to give you those capabilities, I just give you my table, and you have the same level of capability. For example, forking a process involves giving my capabilities to my child process. All right. So that's similarly, let's say memory management. So virtual memory. So you basically say that what all areas of memory are you allowed to access? This is kept per process. So it's a capability list per process. in general, the advantage of capabilities is that it's very easy to delegate. So you can, if I have some capability, I can give you the same capability by just giving you access to the same table, basically, right? The other thing is capabilities are also a little more secure in the sense that only if I have a capability can I even name the system, right? Name the object. Right? So capabilities are also used as a way of naming the object. For example, if I have, so for example, virtual memory. So I can name this particular location because I have a capability of accessing that particular location. Another process who doesn't have the capability of accessing this location will not even have the name or the way to access that particular location. So in general, capabilities allow private namespaces. So basically, you have a namespace for this process or namespace for this user and a namespace for that user, and this user doesn't even know that those files exist, or those resources or those objects exist, which are in your capability list. Whereas if you have access control lists, the entire namespace is public. Okay. So capability systems discourage visibility. Namespaces are private by default, and so they are also thought to be more secure than access control lists in that sense. And there have been experimental systems that have tried to use capabilities for file systems instead of access control lists, but they tend to be a little clumsy for file systems, but they're used for other things like virtual memory systems, etc. They're also used in distributed systems a lot, and capabilities are also implemented using cryptographic means, right? So, for example, a capability could involve a signed key or a signed certificate. So, if let's say I got a if I want to authenticate to somebody, I can use a certificate from somebody. So if I want to prove my authorization to access a resource, I can show a certificate from somebody else to say that I can access this particular resource, right? So that certificate, so capabilities can also be implemented using cryptographic means, basically. Okay, finally, enforcing access. And for a kernel, so what does access enforcement mean? So we've seen ways of saying that here is how you authenticate. You authenticate using passwords or badges or some biometrics or whatever. Then you have some way of authorizing, which includes access control lists or capabilities. Access control lists or capabilities, and depending on and there's a trade-off on how much space you want to take to represent this stuff, and how much generality you want. And we have seen an interesting example of Unix versus Windows. And then you have some way of ensuring that these things actually are obeyed, right? So this basically means that some part of the system should be responsible for enforcing this, and this part of the system should have total power on everything. Right? So there has to be some part of the system which has total power, and it's basically and this part of the system is checking and saying yes or no to access controls. And for an operating system, this part of the system is the OS kernel, basically, which has total control and is going to do authentication and authorization. So let's look at some attacks. So why do let's see, what are some kinds of attacks that happen? What does a security attack mean? So we keep hearing that XYZ, there's XYZ vulnerability, there is this attack and that attack. What do these things really mean? Basically, an attack means that a user has, firstly, it basically means that a principal has been able to do something that he was not authorized to do. And the most common way of doing an attack is basically what are Trojan horses. Right? Trojan horses are basically derived from the mythical tale. A Trojan horse basically means that a useful program that was supposed to do something legal and meaningful is subverted to do and had privileges or had higher privileges than what you have, is subverted to do something that it was not supposed to do. Right? So that's what a Trojan horse means. So let's see what are some ways of implementing Trojan horses. Well, let's take the extreme case. If you could potentially subvert the kernel, that's the ultimate Trojan horse that you can have, because that has the ultimate power. And if you can subvert that, the access control enforcement engine itself, then you have basically done, you can bypass everything else. Similarly, you know, if you could subvert a program that has a setuid bit set, then you can get control over that particular program's resources. Many programs, you know, especially in the older days, so many programs in our systems run with setuid bit set and owner as root. Okay, so which basically means that this program is going to execute as the root owner. The root will execute with root privileges, but anybody can invoke it, right? So let's you know, let me give you some example. So let's say, you know, there's a program called mail, right? That I can give some file to it, and it will copy it to the destination user, it's mailbox. So let's say there's a program that I provide in my system that's called mail, that says basically that takes an argument which is some text or some file which contains some data, and I say I want to mail this program to this particular principal, and what this program is going to do is copy that data to that person's mailbox. So let's say this is the program. So this particular program in the older days would run using root privileges, because this this program will be a program which will be owned by the root user and will have the setuid bit set, because this program requires the capability, because I can name anybody in my destination, in my recipient field, and so this program should have the power to write to anybody's mailbox, and so this program for that reason needs to run with the root privileges, at least for some time, and with the setuid bit set. So if I could subvert such a program, then I can basically do anything that the root user could do, and there are many types of attacks which are not the subject of this course that can allow. So there are many kinds of common bugs in programs that they were very common 10 years back, not so common today. So it's harder and harder to find bugs in programs that can be subverted, but it was very common to do that 10 years back. And if you could identify the bug, you could exploit it to actually ask the program to behave in a certain way which the programmer didn't expect it to behave. In general, when you have programs of this type, you should follow what's called principle of least privilege, which basically means that if there's a program that's running, so if you have a large program, let's take the example of the mail program, then it should try to run with this mail program has a setuid bit set, so it can either run with root privileges or run with my privileges. So the program should run with the least privilege at any time. So least privilege is required at any time. So for all the operations that don't require root privileges, at that time the program should be running with my privileges. So basically what that means is all the code that gets executed during that time, if there's a bug in that code, then there's no problem, actually there are fewer problems as opposed to if you run all the time with the root privileges. That's it. Okay, right. So with that, let's finish, and we're going to discuss another topic next time, which is called scheduling. And all right.